Good morning. Today begins week 3 of our remote learning. Going to go into a new subtopic in our kinetics and equilibrium chapter. If you got your books, take them and turn them to page 142. And we're going to delve a little bit further into equilibrium. In regards to equilibrium, we've talked about it before in two regards: phase equilibrium and solution equilibrium. We're going to add chemical equilibrium and factors that affect those today. You're looking at page 142. You see the word equilibrium there. If you go to like 7th line down, midway through where it starts, I would underline this or highlight, whatever you generally prefer to do. When both the forward and reverse reactions occur at the same rate, the condition is called equilibrium. An equation representing equilibrium uses the double arrow instead of the single arrow to show reactions are proceeding in both directions. We talked about this in terms of dissolving and crystallizing, evaporation and condensation, melting and freezing, and even in sublimation, given the right temperature, you can both be solid to gas and gas to solid, given the right set of temperatures and conditions. Less talked about, less observed, but it is a possibility. If we look at the diagram on the top of page 142, figure 8-7, you're going to notice there's two jars filled with water. The first jar, the one on the left, is uncapped. And notice it shows the water molecules evaporating, going into the gas phase, and leaving the container, increasing their entropy as it would. Entropy, you might say, what's that? That's tomorrow's lesson. But leaving the container and spreading out throughout the universe, increasing its entropy. That's what entropy refers to, the randomness or chaotic state of the universe. And then the one on the right, the capped one, making it a closed system, those will evaporate. And then, since they can't leave the container, they're going to recondense down into the liquid state. Evaporate, condense. Evaporate, condense. That's equilibrium. Equilibrium has actually been proven by the use of radioisotopes. So if you have liquid water there and you have evaporation going on, there's no radioisotopes of water in there. If you would add a radioisotope of water, what would happen? Those water molecules would evaporate. The gas eventually would become somewhat radioactive. Or if you introduced radioactive water vapor, the liquid would become radioactive, showing that it's going to evaporate and then recondense, evaporate, recondense, etc. All right. If we go down to the two equations at the bottom of the page under phase equilibrium with water, I would circle both of them. The one on the very bottom of the page, that's the one that's going on in the containers in figure 8-7. If we go over to page 143 now, I would underline that first sentence right after the word solution equilibrium on page 143. Solids dissolved in liquids exist in equilibrium. The solution would be saturated, that first sentence. Okay. We have two examples there. Sugar dissolving into water and then recrystallizing, but there has to be solid sugar at the bottom and the solution has to be saturated. Because if it's not saturated, it will dissolve until it's all gone and won't recrystallize. And then at the bottom, that's actually the soda or seltzer equilibrium. Carbon dioxide gas, when your container is sealed, closed system, the carbon dioxide stays in there. You do not see the formation of bubbles. When you open the cap, the gases can leave. We don't have equilibrium forward and back. The gases will continue to escape until your seltzer or soda goes flat. So those two examples of solution equilibrium. Down below, we have examples of chemical equilibrium. All right, you can circle that one. It says CH4 plus H2O gives 3H2 plus CO. You can circle that reaction. Okay, that's a chemical equilibrium. Why is it different from what we refer to as phase equilibrium and solution equilibrium? On both sides of the arrow, this doesn't have an equilibrium arrow. They could have drawn it with that, but we're not going to correct that right now. what's on the left side and the right side of that equation are different. So it's chemical. The other ones are physical because the formula is left and right. It's still water, but in both phases, it's sugar, one in the solid state, one in the aqueous state. Okay, it's still sugar though. All right, what happens is drawn for us in these two little pictures here. All right, actually, it's two pictures. The third picture is the first two pictures superimposed on the same set of grids. All right. As we have a chemical reaction happen, all right, I'm looking at that first one that says forward reaction, figure 8-8, the first diagram. It shows reaction rate versus time. When the reactants are in their highest concentration, the reaction is going to change its concentrations quickly, right? It's going to react faster. But since it's reacting, those reactants are going to leave and they're going to go in lower and lower and lower concentration till the point where the reaction appears to stop. It really doesn't stop. It reaches equilibrium. The second little box there, it says for the reverse reaction, notice it starts at 0 at the bottom of the grid because in the reverse reaction, your products are unreacting to go back to whatever the reactants were, the reverse reaction, and they increase until the point of equilibrium. If we take those two and superimpose them, they reach a point where they both flatten out. They don't have to superimpose. You could have two different lines. There's one on the next page that I'll point out, or 2 pages from here that I'll point out where they don't superimpose, but they do reach a flat line. That flat line is equilibrium. In this one, the flat line equilibrium shows concentrations of products and reactants being the same. That's the significance of them being one line. That's rare if ever happens. It probably never happens, but it can. They've drawn it this way here. They've shown you the most rare case as the example. Okay. Actually, if we can actually turn to 145, I'm going to skip the stress stuff for a moment. I want to go back to the little diagrams. There's a more realistic look as to what you would see if you saw a concentration time diagram for an equilibrium reaction. Notice the reaction is at the bottom. See, it says just underneath figure 8-9, it says CO2 plus H2, right? Those are your reactants. They're going to decrease. And the CO and the H2O, those are your products. They're going to increase. I would write little symbols here like I just did. Can you see that? Right there. Okay, and then if we look, we see the top line starting at a concentration of 1 for the CO2 and H2. Since those are reactants, they're decreasing. Our products, at the beginning of a reaction, products should be 0. We don't have any. They increase to a point, so you see the CO and the H2O. And at the same time, interval 2, both those lines become straight and level. That shows the equilibrium point. The concentrations of products and reactants do not change. The forward reaction is still progressing. Okay? All right. This was just Le Chatelier's principle. There it is. Okay. I'm going to head back to 144, start talking about Le Chatelier. And I think I'm going to give you an example to explain it and just talk about the things that they have here very briefly. And I'm going to give you a summary of the direction of equilibrium changes that we would apply to Le Chatelier's principle. So just follow me for a moment over to my board. All right. We're going to have a chemical system, and all right, we're going to have a chemical system here, and I'm going to give you a very simple look at the concept of equilibrium. Stay home. Go out. All right. Now, there's a certain balance between the time that you're going to stay at home and or go out. In our present time, okay, our time to stay home is going to increase. That means this is going to be a shift left. Let me give you the condition for shift left. COVID-19, to use something current, right? We have COVID-19 that we have to worry about. So what this is going to do, it's going to cause a shift to the left. We're going to spend more time at home and less time out. All right? But let's say, for whatever reason, we're sitting, like this past weekend, the weather wasn't that great, so maybe feel the need to go outside, walk around the block or whatever. Maintain social distance, of course, but go outside, walk around the block. Wasn't that great this weekend because there was a lot of rain. Some of it was heavy at times. No one really wanted to go out. But let's say it's clear, sunny, warm, right? Those are our conditions. That's going to cause a shift to the right. In shifting to the right, the time that we spend out would be more. That means the time that we're going to spend in the house would be less. In shifting the position of equilibrium, in the direction that we determine the shift to go, either reverse or forward, in the direction of the arrow that we point that arrow, whatever is on the side of the arrow where we're pointing, all those things increase. If those things are increasing, where are they coming from? They're coming from the things on the opposite side. So if we're getting more products, we have to get more reactants. If we have reverse reaction, or reactants are reappearing, our products then would have to decrease. So that's what a shift of equilibrium means. And we're going to do it chemically, and I'm going to tell you how equilibrium will change with chemicals. If you're looking at the textbook section, it says concentration changes. And there are two examples underneath it in figures 8-2, 8-3. I'll discuss them with you. And then there are some practice problems at the end. I might do a couple or some of those if I can. Let's see. All right. For concentration, the only way that you can solve a problem in regards to concentration is dealing with one chemical formula at a time. So I'm going to give you rules for increasing. If the question ever asks or involves a decrease in anything, you're going to do the opposite. So here are the rules for increasing, okay? Increase in concentration, I'm going to call it increase in one formula. You're going to go away. You're going to go to the other side. All right? The next one calls for, now I'm on 145. I'm not doing the examples. I'm on 145. Changes in temperature, okay? All right? I'm going to call this increase in temperature, okay? You're going to go away from heat. I'll explain what that means in an example. There is an example on the bottom of 145. All right? The next one says pressure. The pressure one is a little bit more difficult because we have to start calculating moles of gases. The moles of gases will be based on the coefficients of the balanced chemical equation. You have to watch if there's solids and liquids or the aqueous condition. Those do not count as gases, so they're going to be excluded. Okay, so it's increase in pressure. You go into less gas. And the last one, not increase, add, whatever, add catalyst. Okay. We're going to learn that the catalyst doesn't shift the position of equilibrium. In reality, it's really not a question, but they do pose the question. And the answer to the question in regard to the catalyst being added is that the catalyst doesn't cause a shift in the equilibrium. So add catalyst, no shift to equilibrium. So what does the catalyst do? You arrive at equilibrium faster. Okay, we arrive at equilibrium faster. So the pressure change statement is on page 146. And the effect of the catalyst is like the last section of notes before the review questions that we're going to try and do on page 147. All right. So let me see if I can do some of the examples in the book. You can follow along. And then maybe I'll do questions 18 to 24 on 147. All right. All right. If we can look at 144, it says effective increasing the concentration of NH3. We have this current equilibrium existing. It says NH3 plus 5O2 in equilibrium with, that's the double arrow, 4 NOs, 6 H2Os, and heat. Okay, it says at the very top of the line, effective increasing the concentration of NH3. NH3 is on the left, right? That's your one formula. If we add that as a stress, it's going to move away. So since it's on the left, away from the left is the right, so the reaction is going to shift to the right. That's why we see the arrow there pointing right on the system shift. So by adding the NH3 and shifting to the right, we've said that we've added NH3. That's artificially added. So we're not going to talk about the change in NH3, but we will talk about the O2. The O2 is going to decrease because I added an H3. And since I added an H3 and NH3 uses O2, what does the NH3 and the O2 make? It causes an increase in the NO, it causes an increase in the H2O, and it causes more heat because the reaction is an exothermic reaction. It produces heat. Adding NH3 will drive the reaction to the right. Since it's on the left, it will drive everything to the right, increasing all things on the right. Now, if we decrease, I gave you the increasing rules on the board. If it's decreased, you're going to have to do the opposite. Notice this table 8-3 shows the change when we decrease. It says the effect of decreasing NH3. Okay? So the NH3 is removed. That's why it says minus NH3. Well, taking the NH3 away is a stress. Reactions will move in the directions that will tend to alleviate the stress. So what's going to happen, that NH3 that was taken away, some of it's going to have to be replaced. So where can we get the components to make NH3? You're going to get it from the NO and the H2O. Notice now the system shift is to the left. The NO and the H2O are going away to replace the NH3 that was removed. And in replacing the NH3, you're going to produce more oxygen. Okay? That's shifting. Temperature works almost exactly the same. If we look on bottom of page 145, same reaction. Notice where the heat is. The heat is on the right. It says in the top of the problem, it says table 8-4, effective increasing the heat. Okay? So if you increase the heat, stresses the heat, it's going to move away from the heat. Increase the heat, move away from the heat. So that means shift left. You see the system arrow? It shows it's shifting left. That means we're going to get more NH3 and more O2, and the NO and the H2O, those are going to go away. Turn the page, look at the example top, right? Decreasing the heat. If it says to increase the heat, move away. If it's decrease the heat, we're going to move back towards the heat. So, given the same reaction, heat's on the right. If we decrease the temperature, that means we're taking heat out. It's going to have to move in the direction that produces more heat, favoring the exothermic reaction, right? So it's going to go to the right, okay? Creating more heat. That means the NH3 and the O2 are going to be consumed. You're going to get more NO and more H2O to replace the heat that was removed. It says minus heat there. That's because the heat was removed, so we got to replace that heat. You're never going to be able to replace all of it, but you will replace some of the heat that was removed. Okay. There are no examples for pressure here, like in the little chart, which is nice. I will talk about a couple of the examples. Mid-page, you see the CO2 and the CO2AQ reaction right there. The CO2 gas, CO2 aqueous in solution. Pressure will affect that reaction. If you increase the pressure, it's going to go to the side with less gases. Which side has less gases? The right. So the CO2 would become dissolved in the liquid. If you decrease the pressure, it'd shift to the left, increasing the concentration of gases. I just got like a nice little demo for you. I just thought of it right now. Hold on. I hope I didn't shake this up too much on my way back and forth to the refrigerator. Guess where I shop? Okay. Look, this is pressurized. I cannot squeeze that. You don't see any bubbles in here. Under pressure, right, high pressure, the gas goes into the liquid. I open the top. Listen. You can probably hear the gases venting. And now, right, you see the bubbles being produced? Okay. Those bubbles are being produced. The bottle is no longer pressurized. I can squeeze it. So under low pressure, the gas is going to be produced. Low pressure, given the reaction the way it's laid out, low pressure goes to more gases. That would be the left, producing the gas bubbles that you see being produced here. Close it, seal it. You're going to have to wait a couple of minutes for it to pressurize. I'm not going to do that. But then it's no longer going to produce bubbles. The bubbles will come out once I knock them off the sides, and there's going to be no more bubbles being produced on the side. It's going to come to equilibrium again. Excuse me. Down below, the N2H2 yield NH3 reaction. There's 4 gases on the left. There's 1 N2, 3 H2s, and then there's 2 NH3s on the right. So 4 gases on the left, 2 gases on the right. High pressure, that will shift to the left. Low pressure, high pressure, that will shift to the right. The right side has less gases. Low pressure, that will shift to the left, giving you more N2 and more H2. Right? And then the last thing is a catalyst. Remember, a catalyst just doesn't give a shift. It gets you to equilibrium faster, but it will not change that point of equilibrium. As a matter of fact, if the reaction's already at equilibrium, then the catalyst really will not do anything. It'll simply just speed the reaction up, but it's not going to change the position of equilibrium. All right, you know what? What I think I'm going to do is this. I'm going to ask you guys right now on your own to do 18 to 30. Tomorrow, I'm going to discuss the answers to 18 to 30 with you. They're all shifting questions. That'll be my opening. And then I'm going to give you a very short lesson on entropy. Entropy is actually pretty easy. And then I'll try and answer questions through 39. And then I'm pretty much going to be finished with this topic. I don't know if I'm going to bother with the equilibrium expression. They really haven't put questions on the Regents exam on it for a very long time. It's easy, but I don't know if I'm going to take time with it. I'll definitely do entropy tomorrow, and then I'll start assigning you some practice questions that we can go over. Have a good day, guys. Bye-bye.